At the beginning of 2022, the Hubble Space Telescope discovered the farthest star ever seen by humans. Astronomers named it Arundel, meaning morning star in Old English. In 2023, the Webb telescope replaced its predecessor, continuing to observe and explore this ancient star. Webb's near-infrared camera, NIRCam, revealed that Arundel is a massive B-type star, twice as hot as our Sun and shining 1,000,000 times brighter. Given its age, Arundel could be one of the first stars formed after the Big Bang. Its appearance has sparked a new wave of interest in the scientific community. Researchers have been actively pursuing giant stars like Arundel for over a decade. What processes led to the formation of these stars and the first galaxies? Will we have the opportunity to witness the universe's development immediately after the most tumultuous period? All these questions will be addressed in today's accidental appearance video. Arundel is part of the Sunrise Arc galaxy, located approximately 12.9 billion light-years away from us, existing in a region of space only 900 million years after the Big Bang. Due to the universe's ongoing expansion at an increasingly rapid pace since the Big Bang, this star is currently situated at a distance of 28 billion light-years from Earth. Thanks to the phenomenon of gravitational lensing, astronomers have discovered and observed this distant star. Both Hubble and Webb telescopes were able to detect Arundel due to its fortuitous alignment behind a cosmic wrinkle in spacetime created by a massive galaxy cluster known as WHL 13708. On March 30, 2022, NASA announced that Hubble discovered Arundel through a phenomenon called gravitational lensing, where the gravitational force of a massive object in front acts as a lens, bending the structure of space and time as light passes through. The JWST team also employed a similar strategy by harnessing the space-bending power of the gravitational cluster WHL 13708, coincidentally aligned with Arundel. Valued at $10 billion, the infrared light observation of the universe provided a glimpse into Arundel last summer, shortly after commencing scientific operations. Arundel appears as a single bright point in galaxies, unlike other features that often appear multiple times due to gravitational lensing. Arundel only manifests as a single point, even in high-resolution infrared images captured by the Webb telescope. Based on this, astronomers have determined that the object is magnified by at least 4,000 times and is, therefore, an extremely small star located farthest away ever detected. It was observed 1 billion years after the Big Bang. The previous record holder for the farthest star was discovered and observed by Hubble, and it existed approximately 4 billion years after the Big Bang. Usually, stars with significant mass have companions. However, astronomers do not expect Webb to reveal any companions of Arundel, as they would be very close together and indistinguishable in the sky. Nevertheless, based solely on the color of Arundel, astronomers believe that they see signs of a cooler, redder companion star. The light emitted by this companion star has been stretched due to the universe's expansion to longer wavelengths beyond what Hubble instruments can detect, hence, it can only be observed with Webb. Another research group using Webb recently identified a gravitationally lensed star named Quilla. This red giant star was observed 3 billion years after the Big Bang. WHL 13708, situated between us and Arundel, acts as a magnifying glass. The galaxy cluster is located in the constellation Aquarius. Webb's NIRCam also reveals other noteworthy details in the Sunrise Arc, the galaxy with the highest magnification ever detected in the first billion years of the universe. Features include regions of young star formation and older star clusters with diameters as small as 10 light-years on both sides of the fold, with maximum magnification passing through Arundel. These features are reflected by the distortion of the gravitational lens. Stars forming in the elongated region appear to be less than 5 million years old. The smaller dots on either side of Arundel represent two images of an older, more stable star cluster estimated to be at least 10 million years old. Astronomers determined that this star cluster is bound by gravitational forces and likely still exists today. This provides us with a glimpse of what star clusters in our Milky Way might have looked like when they formed around 13 billion years ago. A team of astronomers is currently analyzing data from Webb's near-infrared spectrograph, NIRSpec, to learn more about the Sunrise Arc galaxy and a star named Arundel. This analysis will provide accurate information about the galaxy's components and distances. After Hubble discovered Arundel, Webb used a similar technique to detect other distant stars. Although not as far away as Arundel, these findings have opened up a new area of astrophysics and provided scientists with a new way to study the early universe when galaxies were once the smallest detectable objects. The researchers hoped that this could eventually lead to the discovery of one of the first-generation stars made only of the raw elements created during the Big Bang, such as hydrogen and helium. Even though Webb only caught a brief glimpse of Arundel, the team has gathered enough information to begin describing the characteristics of this remarkable star. Arundel's rare alignment with WHL 01378 means that the star is directly on or very close to a curve in spacetime, resulting in maximum brightness. This makes Arundel stand out against the overall light of its home galaxy. This effect is similar to the ripple patterns on the surface of a swimming pool, creating bright light patterns on the pool floor on a sunny day. The ripples act like lenses, focusing sunlight to achieve maximum brightness on the pool floor. While other features in galaxies often appear multiple times due to gravitational lensing, Arundel only manifests as a single bright point, even with Webb. Based on this, astronomers determined that the object is magnified by at least 4,000 times and is, therefore, extremely small. Moreover, we are observing it at a point just 1 billion years after the Big Bang. Previously, Hubble had found the record holder for the farthest star about 4 billion years after the Big Bang. Subsequently, another research group using Webb recently identified a gravitationally lensed star named Quilla. Arundel may have a mass ranging from 50 to 100 times that of the Sun. Due to its substantial mass, the star likely underwent a supernova explosion only a few million years after its formation. With this mass, it is almost certain that it did not survive until the present day, as larger stars tend to burn fuel more quickly and thus explode or collapse into a black hole sooner. The oldest known stars formed around the same time but have much lower mass, allowing them to continue shining to this day. Arundel has an effective surface temperature of about 20,000 K. It is likely a population 3 star, meaning it contains virtually no elements other than primitive hydrogen and helium. This could be a step toward eventually discovering one of the first-generation stars composed only of the raw elements created in the Big Bang, hydrogen and helium. Stars with large masses, such as Arundel, often have companions. Astronomers do not expect Webb to reveal any companions of Arundel, as they would be very close together and indistinguishable in the sky. However, based solely on the color of Arundel, astronomers believe they see signs of a cooler, redder companion star. This light has been stretched due to the universe's expansion to longer wavelengths beyond what Hubble instruments can detect, and therefore it can only be observed with Webb. With its brightness, Arundel is classified as a B-type star. B-type stars are highly luminous, and Rigel in the constellation Orion is an example of a blue giant supergiant belonging to this class. Their spectra exhibit neutral helium lines and moderately strong hydrogen lines. Due to their intense activity, O and B-type stars have short lifespans and tend not to stray far from the region of their birth due to insufficient time. Consequently, they are inclined to form associations with each other, known as OB associations, which are associated with giant molecular clouds. The Orion OB1 association is a spiral arm belonging to the Milky Way. Brighter stars make the spiral arm appear brighter, although there aren't many stars there, and it encompasses the entire Orion constellation. In addition, the classification scale includes 7 other categories: O, B, A, F, G, K, and M. O-type stars are extremely hot and luminous, with a color close to blue. Neos, Zeta Puppis, in the constellation Puppis shines about 1 million times brighter than the Sun. These stars exhibit distinct ionized and neutral helium lines and faint hydrogen lines. O-type stars emit most of their radiation in the form of ultraviolet rays. The majority of the first-generation stars are predicted to be of O-type. A-type stars are more common among observable stars with the naked eye. Deneb in the Cygnus constellation is an example of a highly active A-type star, while Sirius in the Canis Major constellation is also an A-type star but less active. A-type stars appear white. Many white dwarf stars also belong to the A-type category. They exhibit strong hydrogen spectral lines and lines from metallic ions. F-type stars are also active stars, but tend to be main sequence stars, such as Beta Virginis in the Virgo constellation. Their spectra are characterized by faint hydrogen lines and lines from metallic ions, giving them a slightly yellowish-white color. G-type stars are the most common spectral type. G-type stars are perhaps the most well-known because the Sun belongs to this category. They have weaker hydrogen lines than F-type stars, but along with lines from metallic ions, they also have neutral metal lines in their spectra. Supergiants are typically O or B-type blue or K or M-type red stars. Because they are so, it is unlikely for them to be G-type, since these are unstable regions for supergiants to exist. K-type stars are orange-red stars with temperatures slightly lower than that of the Sun. Some K-type stars are giants or supergiants, such as Arcturus, while others, like Alpha Centauri b, belong to the main sequence. They exhibit very weak hydrogen spectral lines, if any, and mainly show neutral metallic lines in their spectra. M-type stars are the most common spectral type in terms of the number of stars. Over 90% of stars are red dwarf stars like Proxima Centauri. Some giants, supergiants like Betelgeuse, and variable stars like Mira also belong to this category. The spectra of M-type stars are characterized by molecular and neutral metallic lines but usually lack hydrogen lines. Titanium dioxide may be abundant in M-type stars. The redness of these stars can sometimes lead to confusion regarding their actual distance, making them appear farther away than they are if an object with a similar temperature, such as a halogen lamp, 3000 K, is placed a few kilometers away. It will also appear as a red light source to an observer, similar to these stars. Each of these spectral types provides valuable information about a star's temperature, luminosity, and composition, aiding astronomers in understanding the characteristics and evolution of stars throughout the universe. The Harvard spectral classification is the most common and easily understandable method of star classification to date. Additionally, astronomers classify stars based on their evolutionary stage and formation processes. Most of the stars we know today belong to generations 1 and 2, while stars of generation 3 have nearly disappeared or are extremely challenging to observe as they are at the boundaries of the Big Bang where modern space telescopes struggle to observe. Therefore, cases like Arundel are exceptionally unique. Without a doubt, Arundel is undoubtedly one of the first stars contributing to the era of reionization. Going back to observe the first 380,000 years after the Big Bang, the universe was a hot mixture densely packed with protons, electrons, other elementary particles, and light elements. Shortly thereafter, the expanding universe was rapidly cooling. Once the temperature dropped to around 4,950 degrees Fahrenheit 2,730 degrees Celsius, protons and electrons could form atoms. However, not all elements were formed during this time, only hydrogen and helium, with oxygen notably absent. Hydrogen and deuterium isotopes accounted for about 3/4 of all atoms, while a few isotopes of helium made up the majority of the remaining quarter. A small fraction, about 1 part per billion, of lithium also formed. In reality, the first luminous objects did not appear until the universe was about 100 million years old. So, for a period longer than the extinction of dinosaurs on Earth, there were no stars, galaxies, or any objects emitting light. The origin of the first generation of stars is known as population 3 stars. Their light is now too faint to be detected by current observatories, hence Arundel is an exceptionally fortunate find. Even the next generation of astronomical telescopes will find it challenging to detect them. However, through the detective work of scientists, astronomers are beginning to understand how these elusive objects lived and died. Computer simulations show that tiny density fluctuations in the early universe played a role as the starting point for massive gas clouds. Without these variations in the structure, nothing would have formed. The entire universe would have evolved into a homogeneous, increasingly thin cloud of hydrogen, helium, and a small amount of lithium. However, thanks to gravitational attraction, these fluctuations became gathering points for massive clouds where gas continued to accumulate. Eventually, these clouds collapsed. In doing so, they heated up to over 1,300 degrees Fahrenheit 700 degrees Celsius. This temperature is too high for a region forming stars in the modern era to give rise to stars. Indeed, if a cloud is hotter by about 10 Kelvin, 442 degrees Fahrenheit or 232 degrees Celsius, the speed of the atoms within it would be too fast for them to bond together and ultimately form stars. But the clouds in the early expanding universe were much larger and denser than the nebulae today. Among them, some hydrogen atoms paired up to become hydrogen molecules. Because molecules are better at emitting infrared heat radiation, the temperature dropped, and the clouds inside could contract further. Each region could be hundreds of times the size of the Sun. With such large masses and equivalent gravitational force, they could overcome external radiation pressure. These masses did not separate as they contracted, so only one star formed from each mass. The result is that the first stars likely had enormous sizes, estimated to be from tens of times the mass of the Sun to 1,000 times the mass of the Sun, and shone perhaps millions of times brighter than the Sun. Astronomers theorize that in addition to their large mass, the first stars were also extremely hot. Their surface temperatures could be 15 to 20 times that of the Sun, and most of their emitted radiation fell within the infrared region of the spectrum. Although supernovae did not play a direct role in the birth of the first stars, events like these are part of the causes leading to their demise. The larger a star is, the shorter its lifespan, so the first stars may have only existed for a few million years or less. Theory predicts that when a star with a mass between 140 and 260 times that of the Sun reaches the end of its life cycle, it will create an unstable pair instability supernova. In the core of such an object, electron-positron pairs disrupt the balance between outward radiation pressure and gravitational forces pulling inward. As gravity starts to dominate, the core will collapse. This causes its temperature to rise, leading to an enormous increase in nuclear heat. In fact, the star explosively blows itself apart without leaving any remnants such as a black hole. In this way, all the elements synthesized by the star, including iron, expelled into space. This seeds the surrounding gas with matter, creating a mixture that will form the generations of stars in the future. Therefore, in a sense, the death of these stars is as crucial to the universe's development as their birth. Currently, scientists are searching for second-generation stars, focusing their efforts in the halo of the Milky Way, a region that includes old stars and star clusters. Population 2 stars are concentrated in the core of our galaxy. Quilla, a red supergiant star, has existed for 3 billion years after the Big Bang. Quilla is also the first red supergiant star excavated from the early universe. It is a colossal, glowing red space monster, a cosmic enigma from the early universe that the scientific team led by astronomer José Diego from the Cabrera Physics Institute believes could be a representative of red supergiant stars. According to SNews, red supergiant stars are the evolutionary descendants of large stars with initial masses between 7 and 40 times that of the Sun. They are stars with the largest radii among all known star types, although not the most massive. As they are a celestial body that has been inflated, stars, including our Sun, towards the end of their lives, will deplete their energy and expand into a new form known as a red supergiant, much larger in size than their original state. After a while, red supergiant stars will conclude their short-lived existence by collapsing into white dwarfs. Returning to the intriguing object mentioned earlier, the entity dubbed Quilla reveals its mysterious nature in the data from the James Webb Space Telescope, primarily operated by NASA with the support of ESA and CSA, the space agencies of Europe and Canada. The James Webb Telescope is currently the most advanced space telescope with exceptional observational capabilities. As a result, the red supergiant cosmic monster mentioned above, located at a staggering distance of 10.7 billion light-years, still falls within the lens of the James Webb Space Telescope. It resides in a massive ancient galaxy cluster known as El Gordo. The star may have collapsed and dissipated into the universe in a supernova explosion billions of years ago. However, due to its extreme distance, the primetime images from 10.7 billion years ago have taken that long to reach Earth's telescopic view. In other words, we are observing the shadow of an object time-traveling from the dawn of the universe. This red supergiant cosmic monster has a surface temperature of approximately 2,800 degrees Celsius, a relatively cool temperature compared to G-type stars like the Sun, causing it to emit a redder light in the universe. The hotter an object, the bluer its light, transitioning from cooler colors towards white, yellow, and orange, with the coldest objects emitting a red hue. About 3.3 to 4.9 light-years away from Quilla is a pair of unclear, diffuse, and greener objects, possibly a star-forming region and also an echo image. With a distance of 10.7 billion light-years, this spectacular object emerged when the universe was only 3.1 billion years old, and it could very well belong to a population that appeared first in the cosmic void. Currently, with the advent of the James Webb Space Telescope, ancient stars like Arundel or Quilla are being discovered more frequently. We are expanding the scope of observation, searching not only for ancient galaxies but also for the first stars of the universe. Future studies hold the promise of bringing many surprises. At present, the best hope for astronomers to directly detect a population 3 star lies with NASA's James Webb Space Telescope, JWST. Despite its 6.5-meter mirror, it might be able to capture a faint flash signaling one of the first stars to become a supernova. If a large galaxy cluster lies between the population 3 star and the JWST, it could act as a gravitational lens, bending and amplifying the light from the star. A 2018 study led by researchers at the University of Arizona and the University of Melbourne showed that the JWST could potentially find some of these first stars if it observes 30 galaxy clusters twice a year over an estimated lifespan of 5 to 10 years. Of course, researchers may dream of constructing a powerful telescope capable of capturing the light of population 3 stars without assistance. Anna Schauer and her colleagues at the University of Texas calculated that a 100-meter wide telescope would be sufficient if placed on the Moon. Their proposed observatory, named the Extremely Large Lunar Telescope, and was published online in July last year. It would be situated within the perpetual darkness of a lunar volcanic crater at the Moon's south pole, isolated from heat that could interfere with its infrared observations. Could this happen soon? Possibly, at least in terms of astronomy.